In this math counts preparation lesson, we're going to be doing a full, in-depth video on analytic geometry. Now, analytic geometry is basically geometry done on the coordinate plane, or the Cartesian plane, whatever you want to call it. So basically, so analytic geometry requires a lot of algebra. You have a lot of equations of lines, etc. So we're going to talk about a lot of those. So we're going to start off with the equation of a line, since that's like the most fundamental part of analytic geometry, is the equation of a line. Now, the equation of a line, we're going to include slope and stuff, so don't worry. So, equation of a line is denoted as, in slope-intercept form, is y equals mx plus b. Now, usually, you might be given an equation in standard form, so you want to convert it to slope-intercept form, because that just makes it a lot easier. So here, x and y are just coordinates, and m and b. M is the slope. And the slope, m, is just y2 minus y1 over x2 minus x1. So this is how you find the slope. So if you want to find the slope of a line, you just take the difference in the y coordinates and divide it by the difference in the x coordinates. So this is how you're going to find the slope. And b, this b over here, b is the y-intercept. So essentially, if I have a line, this is our Cartesian plane. And I have a line. It's like this. If I have a line that's like this almost, let's just say we have a line. Let's just call it a straight line. Assume it's a straight line. The B is where it cuts the y-axis right here. So this is just B, or it's supposed to be a lowercase b, whatever. So this is supposed to be a B. And this point will be in the form of 0, b, because on the y-axis, all the points that lie on the y-axis, x is set equal to 0 because it's right above the origin, 0, 0 over here. And similarly, the x-intercept is where this line cuts the x-axis. There's no special variable for that, and there's no special place in the equation of a line. So you're just gonna have to find the slope and find the y-intercept, and then just find a point that's on the line, and then set y equal to 0, and then find that. So that's the only thing you can really do. But that's how you will find that. And so b is your y-intercept. X-intercept is no special variable. But if we want to call it a, then it's going to be in the form a0. Because yeah, so a0 is basically your x-intercept, I guess, but there's no special place in the equation of a line or basically anywhere in analytic geometry. Now we can also move on to find the midpoint and of two places. So if you want to find the midpoint of 2 points on a line, there's this special formula which you can use, and it's long and requires division, and it's even more complicated than this one. Scary looking. So I have a better technique to finding the midpoint, and this works for anything, okay? Usually you might have midpoints which have fractions and decimals, which is true, you will have some midpoints, but most of the time when it's asked to find the midpoint, it's usually all evenly spaced out. But even if it's not, this technique works. And so basically, if you have, let's say, a point 6, 5, and then it lies in a line, another point on the line is extremely unrealistic, maybe, but I'm not sure. Is I'm just gonna call it 7. No, 7's a bad example. So I want it to be even though if it was 7, this technique would still work. So I'm gonna do 8, 10. That works. So if I want to find the midpoint, if I want to find the midpoint of these 2 points, so what I'm gonna do is I'm gonna see what I'm increasing the x value by. So I'm increasing the 6 by 2 to get to 8. So since I want the midpoint, I take the 2, I divide by, I just cut it in half, right? I take 1/2 of 2, and I just get 1. So I have to increase the x value by 1, so I get 7. Now we're halfway there. We're increasing the y by 5. 5 plus 5 gives us 10. So, and even though this is kind of a bad example, we take this, and I'm going to redo this, actually. So I want this. Let's just say this is 8 and 9. Okay, so we're still halfway there. Now we're increasing 5 by 4 to get to 9. So we're increasing 5 by 4. So if we're increasing 5 by 4, we just cut in half. We want the midpoint. So we need to increase 5 plus 4 is 9. 5 plus 2 is 7. So we're at 7, 7 is the midpoint of these 2 points. It's right in the middle. Is 7, 7. So that's basically the midpoint. You don't need to memorize any formula, just simple. It's pretty much common sense when it comes to this. This rule, the 7, 7, etc. So that's basically all you need to know for lines. Now let's move on to like the distance formula. Here's where it gets a little bit interesting. Distance formula is long. It looks scary at first, but it's not hard to apply at all. So at first glance it might look like scary, but it's not that scary. So first off, this in the slope, for the formula for the slope of a line, we started with y2. This time we're starting with x2 minus x1. And we square it. And then we add. We take y2 minus y1. And we square it again. And then this might look a little bit scary, but now we just take the square root of the entire thing. Now it looks scary. But it really doesn't. So I'm going to give you an example here by applying the distance formula. Let's say I have 5, 4, and like 6, 8. So the distance formula, let's apply it. We're going to find x2. This x2 is sitting right here. And we're going to find x1, so we're going to label these. And I know you already know this in your head, but we're going to do it. x2, x1. So 6 minus 5 is 1. 1 squared is 1. And now I have y2 minus y1. So I have my y2 sitting out here. This is y2. These are 2. And I have this y1 over here. So 8 minus 4 is 4. 4 squared is 16. And 1 plus 16 gives me 17, but I need to take the square root of it, so it's just the square root of 17. And that's my distance. Since 17 is prime, I can't really do anything about it, but that's the distance from these 2 points. So that's basically how you're going to do it. Distance formula is useful, especially when you have this is actually the most valuable tool in coordinate bashing, which you should watch the coordinate bashing video. It was actually a cool technique. So coordinate bashing is where you look at a geometry problem, not an analytic geometry problem, but just any geometry problem, and you take the figure on the geometry problem and you place it onto the Cartesian plane, the coordinate plane, and you assign different coordinates to different points on the diagram, and then you use distance formula, equation of a line, slope, all your analytic geometry tools to chase lengths around. You can't really use it for angle chasing, but you can use it for chasing lengths around, finding lengths. Usually geometry is just finding lengths in MATHCOUNTS, AMCs. AMCs it doesn't have any proof, so it's all just length chasing, some angle chasing maybe. But that's coordinate bashing, and distance formula is useful for coordinate bashing. So you should just check out the coordinate bashing video for more information on that, if you think that's a good technique, which I recommend you do learn it. So distance formula, equation of a line, we don't really have much left to cover because those are the fundamentals. Analytic geometry. I should also mention that we are not covering the equation of a circle yet. So the equation of a circle is not really needed for MATHCOUNTS. So the equation of a circle, it's not really needed for like chapter level math counts. I will cover the equation of a circle in another video, but that's like an advanced analytic geometry, so that's not like school or chapter level. That's more like state or national. So equation of a circle is also useful, but we're not covering that today because this is just basics. So we're getting the basics down: distance formula, equation of a line. So we have distance formula and equation of a line. There's not really too much left, but we need to talk about slopes. So we're going to go more in depth about slopes. Now, slopes are pretty important topic, but we're going to talk about special cases of slopes because there's a lot of special cases when it comes to slopes of lines. So we're going to talk about the special cases of slopes. Now, once you know the special cases, it won't be that hard to just apply them. So we're going to talk about special cases of slopes. So the special cases of slopes, first the slopes of parallel lines. So the slope of a parallel line, they're equal. So if I have a line with a slope of 3/4, and then another line that's parallel to this line, I automatically know the slope is 3/4. And now perpendicular. This is interesting. So perpendicular lines, if I have one line, I'll call it L1, has slope of 3/4, and then another line, L2, assuming L2 is perpendicular to L1, the slope of L2 will just be -4/3. So you just take the reciprocal of the line that's perpendicular, and then you just take the opposite of it. So it's basically the opposite reciprocal. Parallel line slopes are equal. So this is a pretty easy, just apply the corresponding thing based off. And this is the perpendicular line thing is useful for like right triangles. So like if I have like a triangle, let's say like I have an analytic geometry problem with a right triangle, and I have these two lines and I have these 2 points. I can find the slope of this line, and I can find it, and let's say I have all 3 vertices, I can find the slope of this line, find the slope of this line, and then if these are opposite reciprocals, then I know this is a right triangle. So basically, I'm just gonna give random slopes. Let's say this is like 1/2, and I find this slope, and this slope is just, well, -2. Well, I know that this is a right angle. I know that since the slopes are opposite reciprocals, then this is a right angle. This means it's a right triangle. We can use all sorts of cool stuff, obviously. So that's like special cases of slopes, parallel and perpendicular, and these are the ones you should just know. So we've talked about special cases of slopes, so let's move on to the problems. The problems are pretty cool. We do have circles, but we don't need the equation of a circle. So let's move on to the problems. Okay, we're starting off simple. We have pentagon ABCDE has a vertical line of symmetry. What is the y-coordinate of vertex C? So such that the area of the pentagon is 40 square units. Okay, so we have a pentagon, and now you might know some formula for the area of a pentagon, but I don't, and I don't need to memorize some weird formula. So I see a triangle and a square instantly, and I'm pretty sure everyone does because this is a good pentagon because you can break it up into a triangle and a square. Now we already know the area of this square, so we can just go ahead and find the area of the square. We don't need the distance formula because this is just common sense. We're just increasing the y by 4, so this side is 4. So this means the area of a square. The area of a square is 16. So we know the area of a square is just 16. So you have a square down here. We know it's a square because they're equally spaced out, right? Because this distance is 4, this distance is 4. We already know 3 sides now, so we already know it's a square. So square, area 16. We want the area of the pentagon to be 40 square units, and we want the y-coordinate vertex C. So I'm going to focus on this triangle. This triangle has this base over here is 4. The square is 16, so I'm just going to instantly just subtract off the 16. So I'm going to do 40 minus 16, which I'm going to have 40 minus 16. Now you can probably try to do this in your head. This is like 4, and this is like, I think 24. So, and you can obviously check 24 plus 16. So 24 plus 10 is 34. 34 plus 6 is 40. So yeah, you can also just do the addition out if you want, but I already know this is correct. So now, all we need to do is we need to check the area of this bigger triangle right up here. So the area of this bigger triangle right up here, this area must be 24. Now we already have the base, and we know the area for the triangle is just half of base times height. So the base is 2, half of 4 gives us a 2. So we know the half of 4 gives us a 2 times some height needs to give us, I'm going to call the height x, needs to give us, well, we want the area of this to be 24, since this must be 24 and this is 16. And this half of 2, and then this must be 24. Yep. So the area of a triangle must be 24, so then x is just 12. You just saw this, and x is 12. So that means this height must be 12. So that means this right here, to this point, I'm just going to do the worst height ever. So this height should be like 12. Alright, this height is 12. And we don't care about the x-coordinate, we only care about the y-coordinate. So this height is 12. So we can just check this. 12 times 4 is 48. 48 divided by 2 is 24. And 24 plus 16 gets us to 40. So the area of the pentagon is 40 square units. We want the y-coordinate of the vertex C. So we just go up on this y-axis until we hit 12. So we just go over here and go up 12. We don't really need the midpoint, but we could use the midpoint if you wanted to find the exact coordinate value of C, but we don't need to. All we care about is the y-coordinate. So we're going to go up. Now this is just 12 up from this. So 12 up from this, we're going to hit some point over here that's like something. We know the y-coordinate is 16. And we can check it's 16 since if I go up 12, 12 plus 4 is 16. So this point is like right over here. This point right here. This point is just 0, 16. This point right here. And I don't know, let's call it like, we don't have a G yet. Let's call it point G. Up here is 0, 16, and that means the y-coordinate is 0, 16. So, yeah, and it matches up with this height. So that means the y-coordinate is just 16. Alright, we started off simple. That was pretty easy. So let's move on to something a little bit harder. Okay, this one is a little bit harder. So we have a line is tangent to a circle at the point. We don't even have a picture now. A line is tangent to a circle at the point 2, 5. A parallel line is tangent to the circle at 8, 13. What is the common slope of the two lines? Express the answer as a common fraction. So I'm just going to go ahead and do a rough sketch. Now, do not ever waste your time in the actual competition drawing the tick marks on the coordinate thing. Just draw a rough sketch of what it looks like. That's what I'm going to do here. So we know we're dealing with like quadrant 1, so I'm just going to only draw quadrant 1 out. And we know it's like 2, 5, so 2, 5 is like somewhere over here, I'm guessing. That's like 2, 5. Yep, 2, 5. And then a parallel line is tangent at 8, 13, so that's like right up here somewhere, I'm guessing. And then we have a circle, so the circle is obviously like passed through these points. And this is just a rough sketch of what the circle might look like. So the circle's like right over here. And I know this is like a bad circle, but who cares? So, and we have, this is a part of a line, which is tangent to a circle. So this is part of a line that's just tangent, just sitting up here, and it's tangent to the circle. And then we have another line, and I'm going to redraw this line because it's like badly drawn. So this point is 2, 5, as we know. 2, 5. And then we have a line which goes through it. So that's like, I guess the line's like right along here, and it goes like that. And it goes like this. And then we have another line which is parallel to that line. It's tangent as well. So these two lines are parallel. And we want the common slope. Well, as always, you should be watching the previous geometry videos and previous math counts preparation lessons before you move on to the next one, because they're in order for a reason. Now, I see this 2, 5, this 8, 13, and I see parallel lines, and I see tangents. Now, I see these 2 points, and I think of radius, diameter. So we're going to draw this segment which connects these 2 points. Draw a segment connecting these 2 points. And now check out this segment. This segment is a line which contains 2, 5, and 8, 13. It contains these 2 points. We're asked for the common slope of the 2 lines, and since these lines are parallel, we know their slope is the same. Now check this out. We know from the last video that a property of tangents are that if we draw a segment to a point of tangency, like this one, we have a right angle. So we have a right angle over here, and we have a right angle over here. So these are right angles. Now, how is that useful? They're perpendicular. This segment over here is perpendicular to each one of these lines, and they have the same slope. So now we have a strategy. Our strategy is find the slope of this segment connecting these 2 points, and then we just apply the property of perpendicular slopes. So let's go ahead and do that. Let's start off just by finding the slope, 8, 13, and y2 minus y1, 13 minus 5 give us an 8. So I immediately have 13 minus 5 giving us an 8. And I have 8 and 2 gives me a 6. And we can simplify this. So over here we just have 4, 2 times 4 is 8, and 2 times 3 is 6. So we have 4/3 slope. The slope of this line and is 4/3, and now we can find this common slope because these are perpendicular. So opposite reciprocal, we take the reciprocal, and then we just take the opposite, which is negative. So our answer is -3/4. We often apply different things we've learned throughout math to different things. Like over here, we apply the properties of tangents. These are just tangents. These are just 2 tangents which go 2 points. So these are tangents, and we apply the properties of tangents to the problem. Now, let's go ahead and try another problem. This one was pretty easy if we just draw an accurate diagram. Let's see about the next one. Next one, we didn't really get a picture here either. One line has a slope of -1/3 and contains the point 36. Another line has a slope of 5/3 and contains the point 30. What is the product of the coordinates of the point in which the 2 lines intersect? Okay, so it looks like we're dealing with a lot of algebra here, even though it looks like a geometry problem. So in the last 2 ones, we've been doing a lot of geometry. This one's all geometry, no algebra required in this one. And the last one over here, this was also a lot of geometry. Now we're shifting over to the algebra, since analytic geometry is a mix of both, and there's many ways often to come to the answer. So this one, we're going to take an algebra approach. So we have a line with a slope of -1/3. So I'm going to find the equation of both lines. So it has a slope of -1/3. So we're going to start with the equation of a line. Slope is 1/3. x plus b. And contains the point 3.6. Another line has a slope of 5/3. Okay. So we're going to complete 5/3 x plus b. There we go. So we have these two equations. And this one contains the point 3.6. So when x is 3, y is 6. So now we can just, when x is 3, so negative 1/3 when x is 3, y is just 6. And these cancel, so we're left with negative 1 plus b equals 6. And now we can just figure out from that b equals 7. So we found one piece of the problem. We know that b, which is the y-intercept of this line, is just equal to 7. So we found that b equals 7. So we found b equals 7. We've completed this equation. Let's go on to this equation. We know this contains the point 3.0, so that's the x-intercept. So when x is 3, y is just 0. So these 3's just cancel, and we're left with 5 plus b equals 0, which you can just figure that out. B is negative 5. So we figured out and completed both equations, and now that we completed both equations, we know the first equation. We can just do the first equation to the first equation. Get a little bit more organized. Our first equation is we have y equals negative 1/3 x, and then b is 7, as we recall, plus 7. And the second one is y equals 5/3 x minus 5. So we have two equations. We want to know what the product of the coordinates in which the two lines intersect. So we want to find the point in which the two lines intersect, and then we just multiply the values on that point. So now all we need to do is set these equations equal to each other, and we're done. So I can just set the equations equal to each other. So I have 5/3 x minus 5 equals negative 1/3 x plus 7. I can bring this x term over here, and I have 6/3 x equals 7 5, give me a 12. So this is 12, right? And now I have 2x equals 12. I have 2x equals 12. And now we can just simplify this. We can simplify this because 2x equals 12. That means x is just, we know what x is then. X is just 6. So we figured out what x is. X is 6. 12x equals 6. There we go. So x is 6. And now we can take the 6 and plug it back into any one of these equations and figure it out. So I'm going to go ahead and plug it into the second equation since I don't like dealing with negatives that much. So I have y equals 5/3. And now we can just put the x equals 6 times 6 minus 5. Y equals, then this cancels, so I have a 3 cancels, leaving a 2. 5 times 2 is 10 minus 5, and then y is 5. We have x is 6, y is 5. Our point is 6, 5. So we figured out the point, and now we know that 6 times 5 equals 30, and that is our answer. So we did a lot of algebra here and finally got the answer. And the product of the coordinates in which the two lines intersect is just 30. We didn't need any picture for this one, and there's a reason why they didn't give it to us. So yeah. So that's a basic analytic geometry overview. We covered some good problems. I like this one the best. This one was more on the easy end, but this is on the school sprint round, so obviously. And then we covered a lot of good formulas, theorems, etc. So yeah, that's basically like analytic geometry.